Okay, let's get started. All right, so a couple announcements before we start. First of all, the new homework and project are up, so they're ready to go when you are. There are also now solutions to homeworks 1 and 2, and by that what I mean is when you click Show Answer, which you can still go back and do even for the homeworks you've submitted, you'll now get more text as opposed to just a check mark, and the text will explain why the answer is what it is. So we're going to do our best to make sure that the kind of solution text is there as soon as possible for future homeworks. Waitlist and things like that, everything should be good. I think everybody who was trying to get in is now in, but if you have issues with waitlist or something like that, please come up and see one of us. Any questions before we start? All right. So today we're going to start talking about uncertainty. And in particular, we're going to talk about how to do search when you're not exactly sure what's going to happen in response to your actions. So when you hear about uncertain outcomes, especially since we've been talking about things like games, what might come to mind is, truly random events like rolling dice. And that's absolutely one source of randomness, and for some games like Backgammon where you actually roll dice, that's important. There are other sources of randomness that we'll start to talk about today, and throughout the course we'll see more reasons why there might be uncertainty. But for now, that's an okay metaphor to have in your mind. Let's remember back to the example that made us want to think about probabilities and average case results. And that's this game tree here. And if you remember, in this game tree, you've got two choices if you're the maximizing agent at the root. You can take the left tree or you can take the right tree. And if you're playing against an adversary, so if you have a true minimizing powerhouse agent you're playing against that's actually playing optimally, you look at this tree and you say, if I go left, I'm going to get 10. If I go right, I'm going to get 9. And the 100 doesn't really enter into it. It could be 10, it could be 12, it could be a million. It doesn't matter, because min is going to give you the 9 if you take the right action. But then we thought, okay, you're not always playing against an evil mastermind. Sometimes, again, you're playing against this guy. And this guy makes mistakes. So one reason why you might want to have the right branch is because maybe the agent that is your opponent might actually mess up and you might end up with the 100. Or maybe something is actually truly random. So maybe the agent is picking its moves at random, and then you've actually got a pretty good chance of getting the 100 if they're equally likely. So what we want to do is we want to think in general that when we take an action, it's under our control. Right? We always have full control over the action we choose, so that's always going to be a max node. But other nodes in the tree, they're out of our control. And so far, things that are out of our control we thought of as being adversarial. If we don't control it, it's going to be as bad as possible. And that's a kind of worst-case pessimistic reasoning. Now we're going to start talking about something more like an average case kind of reasoning. So for example, what we might say is, if we're playing against an opponent that's equally likely to choose any of their actions, then we look and we say, well, if these are scores, then over here I'm going to get a 10. But over here I've got this 9 and this 100, so my score is going to be a lot bigger, right? So they don't divide nicely, but I would get 54.5 on average. And so if my opponent's not minimizing but actually picking at random, I should choose the right branch. Now, of course, a couple things are involved in that assumption. First of all, we have to assume they're equally likely, or at least that they're both have a certain probability of happening, because obviously the chances that the opponent takes the 100 are going to influence whether or not it's worth taking the risk of the right branch. So one thing is, how likely is each of these outcomes, right? It's not always uniform. And the second thing is, what am I trying to do? If my goal is to get the highest expected score, the highest average score, I should average. But really, if only 100 will satisfy me and anything less is a loss as far as I'm concerned, well, then maybe you should always go to the right, because the 10s and the 9s are kind of equally bad to you. And so this starts to get into the difference between preferences and utilities and scores, and today we're going to spend a fair amount of time thinking about what all of these things are and what these numbers mean and what it actually means to average them. Okay, so formally, when I draw kind of an arrow pointing down, I think of that as saying this is a minimum node, meaning I'll choose the smallest child. When I draw circles at nodes, these are called chance nodes, and we imagine whenever you see a chance node, all the outcomes are possible with some probability. You say, what probability? Well, that's going to be given to you. For example, you may be told they're equally likely, or it's 75-20 or whatever. All right. If you have nodes that are governed by chance and not an adversary, Then you have a new algorithm, right? And this algorithm is going to be called Expectimax Search. So let's build up to that now. First of all, let's think about why it would ever be that we don't know what the result of an action will be. So if it's an adversary, in some sense we do know what it's going to be, at least provided the adversary is an actual optimal adversary. We don't get the outcome we want, but we can kind of predict it. We know what the adversary is going to do, even though we don't like it. However, sometimes there's true uncertainty. This could be because there's explicit randomness. Somebody rolls dice. Or it could be that your opponents are unpredictable. So for example, in Pac-Man, the ghosts have some noise in how they move, right? And so you don't know what the ghost is going to do. It can also be, and this will become more important when we start talking about applications like robotics, it can also be that your actions, for example, may fail. We'll see more about this in the next lecture. So for example, if you have a robot and it's moving, you give the command move forward, which spins your wheels, and maybe you move forward, but maybe you don't. And you don't really know whether the kind of wheel slippage is going to happen or not. Okay, so these are cases where you know the action you're taking, you don't actually know what's going to happen, and there's multiple reasons why there may be multiple outcomes. So in this case where there are multiple possible things that can happen, we need to figure out what the value of a node is. Before we just say, okay, that's the value of this node is the score that you're going to get under play, which means if it was a minimax value, it's the score you get when confronted with a minimizing opponent. But now you don't actually know the score. So for example, if I take this right branch, what score am I going to get? What should the value be if I head down this node? Well, maybe it's 9, maybe it's 100, maybe it's some mix, and the only way we really know how to mix numbers in a case like this is to average them, but does that even make sense? So we're going to define something for now and then come back to it later and think about whether or not it's actually the right thing. For now, we're going to talk about values that reflect the average case or Expectimax value of a node. So instead of thinking about worst case outcomes, they're going to be average case, and when I say average, I mean a weighted average, and we'll see a little bit more about this in a bit. So here's the algorithm. It's called Expectimax Search. You compute the average score under optimal play. And what that means is you do the same kind of recursive depth-first traversal of the tree as you always did. A max node still takes the max over its children, but the chance nodes, they're like min nodes in the sense that you don't control them, but they're not like min nodes in the sense that rather than taking the worst, you take an average. When you take that average of those numbers, we call that an expected utility. Expectation here means weighted average. And so really kind of procedurally, you're just going to add them all up with some weights. We're going to formalize this kind of problem, the problem that's solved by Expectimax Search, as a Markov decision process. So in some sense, this is something new for this course. We're seeing an algorithm without knowing the class of problems it solves. Let's take a look at the demo of why we want these things. So this is the same grim Pac-Man scenario as last time. So let's start here. Remember, in this scenario, if you're confronted with minimizing agents, that is the ghosts, if you imagine they're doing what's worse for you, then you know that the blue ghost, which is the only one that actually has a choice under ghost movement rules, is going to head towards you. You play out your game tree, and in a worst case outcome, you know you're going to lose, and really the only thing you have control over is when, which means you want to lose as fast as possible, which means even though this blue guy is in fact might be random, you're going to head towards the orange ghost. And if you'll note, the blue guy actually moved away, right? That's a case where the world wasn't as bad as the worst case, but we still acted as if it were the worst case. And this in general is going to be true. We'll see more examples in another demo later, but in general, it's going to be the case that when you assume the worst case, right, sometimes you think the world's going to be really bad, and it's just not that bad. So now this Pac-Man is going to be running Expectimax Search, meaning it's going to look at its score either way and take averages. And in that case, for the first move, the right thing to do is move left because you have a 50% chance of actually winning the game. Now, I don't know what the blue ghost is going to do. If the blue ghost moves down, then we'll continue to eat all the dots and win. If the blue ghost moves up, then in fact, we're still going to lose, and we're guaranteed to lose, and so we'll kind of head back and dive bomb a ghost just to end it. So let's see what happens. Okay, so we took a chance, and we gambled, and so we lose. Now, the reason why left was the right choice is because on average it maximizes your expected score in the game, not that it's guaranteed to work out better. Okay, this is about average case. All right, here's some pseudocode for this Expectimax algorithm. We still have a notion of a state having a value. This is going to be throughout all of these algorithms, and including when we start seeing Markov decision processes. So make sure this is really clear. States have a value, and that value is not what's going to happen in the next step. That value is what will happen in the end if everybody plays the way they play, optimally in the case of a maximizing agent. So the value of a state at a terminal, it's just, that's the base case. It's given to you by the definition of the problem. If the state is controlled by max, then you consider all of the possible successors and you take the maximum. If the state is controlled by chance, then you return an average. So what does this look like? Well, max looks just the same as before. It looks the way all of our maximizations look like, which is you start some bound at negative infinity, and you increase it for each successor, and then you return the max when you're done. The expected value is a little different. You start your weighted sum at 0, right? So this isn't a bound upper or lower. You start it at 0. You look at all the successors. Each successor comes with a probability. What probability? Well, maybe it's uniform, right? If we're rolling a die and it's a fair die. Or maybe it's not. Maybe you have a ghost that comes towards you 90% of the time. Knowing these probabilities is part of knowing the game at the moment. So we compute the probability of the successor, and then we take a weighted average of the value of the successor, which gets computed recursively, and this probability. So it's what you choose, the value at a node is going to depend both on how good the successors are and how likely they are. A really good outcome that's really unlikely, for example, winning the lottery, those two things can balance out. All right, let's zoom in a little bit more. What's it mean to compute an expected value of a state? Well, here's a chance node, right? And here it's 3 children, which in this case are terminal states, so we know their value when we recurse. And the new thing now is each of the arcs has a number. These numbers are probabilities. It's how likely that arc is to happen. Meaning if you play this game again, you might get a different outcome. We're not going to compute the outcome of this game. We're going to compute the outcome of the kind of an average game if we play this over and over again. So in this case, if we want to take the running average, we would say, all right, well, we start with 8. How likely is 8? You have a 1/2 chance of 8, plus you have a 1/3 chance of 24, plus you have a 1/6 chance of negative 12. And we crunch some numbers, and we make LaTeX appear, and we end up with 10. All right, so that's the average value there. It's not the highest, it's not the lowest, it's some kind of weighted average. Okay, let's do a quick example of Expectimax. You should recognize this tree, because we did minimax in this tree. And remember when we did minimax in this tree, kind of the first one was 3 and the second one was 2. A couple of the numbers are a little different, so the numbers work out nicely. Let's see what's different this time. So remember, the left branch used to be controlled by a minimizer, which meant it was worth 3 if it was ever brought into play, right? But now we're going to get an average. And that average is going to be, what's that, 24, 3, 8? Is that right? Okay, tell me if I make a math mistake. The second one is going to have an average of 4. This is assuming they're equally likely, right? If I don't give probabilities, you have to ask what they are. In this case, we're imagining all the outcomes are equally likely. And then over here, that's 7. Okay, so max still looks at these averages and still picks one of them. So we will still get 8 at the root. But this 8 is now backed up by a chance node that has an average utility. Any questions on Expectimax? Like basically no change from minimax, but in some sense, all kinds of new stuff is happening conceptually, which we'll start to get to now. Okay, here's one thing. Remember we used to have this thing, this pruning algorithm called alpha-beta pruning, where we would say, all right, I'm computing some local value, and at some point I can determine that this node is so bad that max won't choose it, and I can skip the other children. Well, what happens when you get to this point in Expectimax? Well, you've computed over here that this node has a value of 8. And now I'm looking at the middle action. I haven't seen all of its children yet. I see a 2. The reasoning used to be, okay, this value might be a 2. It might be less than 2. It might be a lot less than 2, but it kind of doesn't matter. Because if max has an option better than 2, we can stop computing, and we don't have to reveal these question marks here. But how about now? Could this node's average value be bigger than 2? Sure, right? It could be anything. It could be 1,000,000, right? Unless we have some bound on the magnitude of these terminal utilities, it's really, really hard to do any kind of pruning. So in this case, we can't prune here. We have to do more work than we did in alpha-beta pruning because the same bounding arguments don't hold. In short, it's really hard to do any kind of pruning in a tree that's got average values because in some sense, these numbers you're getting are all tangled up. All the kind of leaf nodes contribute. That's different. Remember in Minimax Search, we talked about how there's one kind of leaf at the bottom. There may be ties, there may be many of them. But in general, there's going to be some leaf at the bottom that actually propagates all the way up to the root. Okay, that's not really true here. The root value in an Expectimax tree is a blend of a lot of things. And so it's very hard to prune because lots of things contribute a little bit to that average. Okay. Let's talk about Expectimax in a little more generality than Minimax. What I'm about to say now could have applied for Minimax equally well, but this is very relevant to your project 2, so we're going to talk about it here. In project 2, you're building agents for this game of Pac-Man, and the way CS188's Pac-Man works is Pac-Man moves, then Ghost 1 moves, then Ghost 2 moves, then Pac-Man moves again. And remember, that's a little bit tricky. You're not alternating with your opponent. You're not playing against the ghost kind of hive mind or something that makes one multi-ghost move. Each ghost is doing its thing, and that thing can be adversarial or it can be kind of random and stupid. It depends on what's running each individual ghost. So from your perspective, from Pac-Man's perspective, the root of the tree is a maximization, like always, because Pac-Man's a maximizing agent, wants to maximize its score, or actually now, average score. So what do we get? At the root, we have a choice, and then what happens in response to our choice? Well, in this case, the blue ghost is going to go, and it maybe has a couple options. Now, there's a circle here because the blue ghost in this tree is being modeled as a random agent. So you might say blue ghost is truly random. It just takes each child with equal likelihood. Then the red ghost goes. So in your tree, you have 2 layers of chance nodes before you get to far enough in the future that you have a choice again, and then a max node appears. And in general, there's nothing kind of special about alternating one agent and then another agent. Every layer is a step in time, and whoever controls it, controls it. So if it's a max, it's a max. If it's a minimizing agent, it's a min. If it's some kind of chance thing, then it's a chance. You can have 2 maxes in a row. It doesn't really matter. And at the end, you're going to bottom out in scores, right? Scores of the game when the game ends. And of course, we all know we're going to truncate that at some point and plug in some evaluation function, because you can't search to the end of the Pac-Man game. These numbers we plug in, but we now kind of know what they're supposed to be. They're supposed to be Expectimax values, which is, if I ran Expectimax from that state all the way to the end, what would I get? So it's some kind of average score. Probably not +1, -1, right? It's going to be in the hundreds or whatever Pac-Man scores look like. Okay. Let's talk about this guy. Let's talk about probabilities. So my expectation in this class is you've all seen, in your discrete math background, you've all seen treatment of probability. But we're going to kind of gradually reintroduce everything we need in this course. We'll see a little bit of it today. Most of it will actually come in about 2.5 weeks when we start into our graphical models unit. Okay, so let's talk about probabilities. Formally, and this is stuff, again, that should be familiar to most of you, probabilities involve these things called random variables. We like to think of random variables as an event whose outcome is unknown. So random variables have multiple possible values, just like a variable in a CSP, right? But we don't get to pick the outcome of a random variable. It's going to be one of those values, but with some probability distribution. A probability distribution is an assignment of weights to the outcomes that the random variable can have. So one example of a random variable might be the traffic on the freeway. And I might choose to model this as a random variable t, and the values of t could be none, light, and heavy. Now you might say, that's a crazy way to model traffic. Traffic should be cars per kind of square foot or something. Okay, fine. Now we have t that has many more values. Maybe if it's a continuous value variable, that's fine. It's a different model. Okay, in my model, let's say t is quantized into none, light, and heavy. There might be a probability distribution now where none has a 25% chance, light traffic has a 50% chance, heavy traffic has also a 25% chance. So now we've got 3 outcomes. We know how likely each one is. There are some laws of probability. We're going to need them all in the end. Today, we need almost none of them. Today, all we need to know is that probabilities are non-negative. Okay, so no negative probabilities. And probabilities over all the outcomes of a random variable have to sum to 1. So if I told you that the probabilities of these 3 kinds of traffic were 10%, 10%, and 10%, you would say what happens the other 70% of the time, right? So we might need like a 4th value called Bay Area or something for super heavy traffic, but they have to add up to 1. Okay, probabilities, the important thing isn't kind of, in general, it's not just some number sitting there that we want. It's something we're going to have to compute. That's not going to be true today. Today, the probabilities are kind of just going to be sitting there. But later on in this course, it's not really so much asking what's the probability of traffic, right? That's just some number. It doesn't ever change. It's what's the probability of traffic given some evidence. So we've got some evidence, we've got some variable we'd like to reason about, and so we'd like to be able to do things like compute the probability of heavy traffic might only be 25% kind of normally, marginally, given no information, but given that it's 8 a.m., maybe it shoots up to 60%. So being able to kind of compute what probabilities are given evidence, That's the key thing we're going to do in this class, and we're going to start doing it in about 5 lectures. And we'll talk all about that in great detail later. Today, we don't need to do that. Today, the probabilities are just kind of sitting there. Any questions on probabilities? You will be like living and breathing probabilities by the end of this course. So, okay. Also, what should be a reminder, expectations. So an expectation is an average, but it's a weighted average. The expected value of a function of a random variable is the average value of that function weighted by the probability distribution of the outcomes. It's a lot of words. It's a totally simple concept. It says, if I want to know how long it takes to get to the airport, then I know that maybe how long it takes depends on traffic, meaning it's a function of a random variable. So how long it takes is going to depend on what value traffic takes. And we know there's 3 possible outcomes for traffic. And maybe for each of these outcomes, we know how long it's going to take to get to the airport. Now, we don't know which of these outcomes is going to happen, so we take a weighted average. And if we do that, we multiply each of these probabilities by the times, we're going to get an average. The units of the average are going to be time, right? We took some linear combination a bunch of times, we get time. So we're going to get something, in this case, we'll get 35 minutes. That's the weighted average. I change the probabilities, I change the weighted average. Okay, so that's what an expectation is. Any questions here? Okay, that should be the end of stuff that you've already seen for today. So in Expectimax Search, we have these chance nodes that say, here are the outcomes, meaning here's what this ghost is going to do, or whatever it is, and we're going to weigh the outcomes by their probabilities. So where do we get these probabilities? It could just be that this chance node controls like one 6-sided die rolling, and so there's 6 outcomes, and they're equally likely unless it's a weighted die or something weird's going on. Okay, so it could just be a uniform distribution because we know something. Or it could be really sophisticated. You might have to sit there and analyze traffic reports and plug and chug a whole bunch of numbers to figure out, given your evidence, what your belief should be. So later in this course, we're going to have to do a lot of computation, given our evidence, to figure out the probabilities. Everything out of our control in general is going to have some probability associated with it, but let's say I tell you the red ghost is actually an adversarial ghost. Well, one thing you could do is you could go in and you could scratch out the circles and you could say, okay, those are min nodes, and that would be fine. That would be a perfectly good way of encoding the assumption that red ghost is adversarial. Or you could say it's still a chance node, okay, but the probability of it taking the adversarial action is 1. So you can always kind of reverse engineer Expectimax to do what Minimax does. It's just a little bit awkward. All right, so what do you do when you're presented with an Expectimax problem? For now, you're going to assume that each chance node is like a little package. It comes bundled along with probabilities. It's part of the definition. So later, you're going to have to do computations. For today, there's a probability fairy. It shows up, and it grants you probabilities, okay? And then I guess it leaves. Okay, so that's not the case in general. Don't get confused into thinking the probabilities are always there at your fingertips. But for Project 2, for these games, they are. It's also the case that just because you're not sure what another agent will do doesn't mean that agent is actually rolling dice or flipping coins. Meaning, like, you're playing a human and you don't know, are they going to take the left path or the right path? Your uncertainty doesn't mean the human steps away from the game and flips a coin, right? Your uncertainty, in some sense, is your problem. It doesn't mean there's any randomness in the other agent. It reflects, in many cases, a lack of knowledge or a lack of a model of the opponent, not that they don't know what they're going to do and need to go find a coin. Okay, let's do a quiz to make sure we got all the stuff about Expectimax and Minimax and all kinds of weird interactions. Okay, so let's say the following. We know that our opponent is not kind of just picking moves at random. It's a reasonable opponent. What this opponent does is looks at the state of the board, so they look at their board, and they run Project 2 or something like that. So they run a depth 2 Minimax. 80% of the time, they do what the Minimax says. Okay, but just to keep you on your toes, 20% of the time, they pick an action at random. Okay, so that's their strategy, and you know it. So they look at the state, they run Minimax, maybe they take the result, maybe they don't. Now your problem is, knowing this, what tree search should you use to predict your action? So you see a state, you're going to do some kind of tree-structured search to pick an action. What should you do? Okay, so find a friend sitting next to you and discuss for a couple minutes, and then we'll see what the answers might be. Okay, let's see what you all came up with. How many people say we should use a Minimax search? Okay. How many people say you should use an Expectimax search? How many people say you should do something totally unlike either of those things? Okay, does anyone want to say something in defense of either Minimax or Expectimax? Okay, I will. I'm going to defend Expectimax. So in some sense, like, the answer in some level is always Expectimax. Expectimax is always an okay answer, it's just not always the most efficient answer. So for example, we could say, we need an Expectimax search. Max nodes, that's easy. I get a choice between the two outcomes. I should pick whichever outcome has the best value. The tricky thing is, how should I think about the value of a node that an opponent controls, right? Because there's two possible outcomes. Which one's going to happen? In Minimax, the worst one happens, but in Expectimax, we take an average. Now, in order to take an average, I need to know how likely each one is. Luckily, I can compute that. So what I have to do is I'd have to say, every time in this depth-first search of this tree I get to a chance node, I need to compute some probabilities. And unfortunately, here's a case where the probability fairy is not going to do it for me. Computing probabilities involves work, right? So at each chance node, we have to like stop and say, all right, what's my opponent going to do? And I do a little simulation of my opponent. We play mind games. So I say, all right, my opponent's going to do this depth-limited Minimax search. Then, with some probability, they're going to take that outcome. Otherwise, they're going to take a random outcome. And so if I kind of work that out, I'll say, all right, if the right action has got an 80% chance of being taken because it's the Minimax optimal thing at depth 2, and then they might move randomly with 20% chance, which means 10% each way. These are the total probabilities. I have to do a bunch of math and a bunch of kind of computation to figure out what they're going to do, but then I get on with my search. So it's going to be slow because there's all these little embedded, nested Minimax searches, but at the high level, it's an Expectimax search. Okay, so you could imagine this kind of thing getting very slow very quickly. Like, what if my opponent thinks that I'm a depth 3 Minimax agent, so I have to run a simulation of it running a simulation of me? Or maybe I should run a simulation of it running a simulation of me running a simulation of it, and just kind of keeps nesting forever. So you can imagine this becomes a disaster very quickly. Typically, your model of your opponent is simpler than your model of you, right? And then if you ever find yourself having to have a model of your opponent's model of you, that's got to be super simple. You can't just keep recursing these things. Except in one case, right? Obviously, you don't want to get into simulating your opponent simulating you, but in Minimax, there's this nice effect that if I'm a Minimax agent and I think you're a Minimax agent that thinks I'm a Minimax agent that thinks you're a Minimax agent, right? You don't get this nested kind of mess. It actually all kind of dovetails nicely into this single Minimax tree. So Minimax is this case where it all collapses into one tree, and it doesn't become super complicated. But in general, Expectimax is always the answer in principle. Sometimes it's not the most efficient thing. Okay. Let's move on. Now we have a bunch of algorithms. We can take a search problem, we can use Minimax, we can use Expectimax. And the difference between these isn't really so much algorithmic. I mean, sure, alpha-beta pruning works on Minimax, but not on Expectimax. But really what changes when you go from Minimax to Expectimax is your assumption about the nodes that are out of your control. So this is more about modeling, right? This is your model of the world. You think they're adversarial, you plug in a mid node. You think they're acting randomly, you plug in a chance node. You think it's something more complex, you do something more complex, which usually means a chance node. Okay, so let's think about why these modeling decisions are important. And what it boils down to is the dangers of optimism and pessimism, right? If you think the world is better than it is or worse than it is, you can make poor choices. So let's think about the dangers of being too optimistic. So if you're dangerous optimism is when you assume things are kind of, chance events when in fact the world is adversarial. The world is out to get you and you think, you've got a decent shot. So, that's like this. You're passing this kind of cave of monsters, and you're like, oh, what are the chances they're going to bother me, right? But they eat things like you, and it's not going to go well. So you don't want to be optimistic when, in fact, the world is adversarial. On the other hand, pessimism can be dangerous too, because you might look at this and be like, okay, we'll always think about worst case. We'll always be pessimistic. Why is it bad to be overly pessimistic? Yeah, I mean, you spend a lot of your time scared, basically. And in particular, you're going to refuse to take reasonable risks, right? And you're often kind of pinned into trying to decide, am I more afraid of the rabbit on the left or the rabbit on the right, and you're just panicking. And sometimes you can make a better decision by just by thinking about kind of the average case of what's likely to happen. All right. Now, of course, this all has to do with exactly how scary that rabbit is and exactly how scary the cave is and all that kind of stuff. But you get the kind of basic idea. So let's see this happening in a demo. So what we're going to do is we're going to load a very simple world. It's got one Pac-Man and one ghost. Pac-Man is going to be either a Minimax or Expectimax agent. So it's either going to kind of assume things out of its control, meaning the ghost is Minimax or Expectimax. So when we say it's an Expectimax Pac-Man, we mean Pac-Man treats the ghost as a chance node, and in this case that means even actions. Okay. Then we can alter whether the ghost is actually adversarial or moving randomly. So let's look at what happens. I'll show you the actual games, although the numbers here are from an average. And let's first take a look. Okay. So here's Minimax. Everybody's Minimax. The ghost is coming for Pac-Man. Pac-Man knows it, so he plans the long way around to kind of prove that he's going to be safe. Okay, so you have to kind of go out of your way to stay safe, but you know the ghost is coming for you, and you deal with it. Okay, so that's one possible outcome. And in that case, the ghost was adversarial, and the model of the ghost was also adversarial. Okay, what happens if you have a ghost that's actually adversarial, but you treat it like it's just random? Well, you look around and you're like, oh, what are the chances it's going to actually head towards me, right? And then you get surprised, and you're like, oh, how bad can it be? And sooner or later you take some risk that doesn't pay off. So that's a case of so in that case, that Pac-Man was too optimistic, right? It's like, oh, the ghost will never come for me, because in the model the ghost usually doesn't, but adversarial ghost. All right, let's look at another case. So we know it was better when you had the kind of adversarial ghost model and an actual adversarial ghost. Here's a random ghost model and a random ghost. So here Pac-Man takes a risk, and it's fine because the ghost is just kind of bumbling around. So that's a case where, again, your assumption aligned with the actual reality, and so things went well. So what's the interesting case? The interesting case is where the ghost is random, but you're still scared of the rabbit, right? You think it's kind of this ghost mastermind. So what do? Right? It's going to bumble around, and you're going to run away. And you're like, oh, what's going on? What is its master plan? It's going to come for me, right? So Pac-Man's sitting here freaking out. Sooner or later, the ghost is going to do something. Okay. All right. So what's the moral of that story? The moral of that story is when your assumptions match reality, that's usually where things are going to be the best. Now, if you actually look at some averages and not just a specific game, what you can see is that if it's an adversarial ghost and you treat it as such, you're going to win, but you're going to kind of get a lower score because you have to go around the long way to be safe. If it's an average ghost and you treat it as such, you're going to win, and you're going to get a high score because you're going to take a risk and take the short path. On the off diagonals here, well, if you're Minimax and it's a random ghost, you're going to live, right? But you're going to spend a lot of time kind of treating it as worse than it is, and so you're going to pay a price for that in your score, right? The danger thing here, in some sense, is you treat the ghost like it's random, and in fact it's adversarial, and in fact, in this case, you lose a lot. But you can see that it's better to be on the diagonal. It's better when your assumptions match reality. And if you have a choice between these, well, it's better to be in a world where you have a random ghost than an adversarial ghost. That's just true, right? But it's kind of out of your control. Given the ghost is what it is, you should model it the way it is. Any questions on that? Yep. Okay, good question. The question is this: why wouldn't you want to do something like observe the ghost, and as you play, update your belief as to what kind of ghost it is, and adjust your model of the ghost accordingly? That sounds like a great idea. It's just something we can't quite yet do, right? We would need, for example, our state representation to include our evidence so far, and we need a way of computing a belief given that evidence. And that's actually something we will absolutely be able to do, but not for a few more weeks. All right, other questions? That was a great one. Okay, so let's talk about some other kinds of games, and then we're going to talk about preferences and utilities. Okay, and when I say other types of games, I still don't mean things like StarCraft. I mean things like Backgammon. So in Backgammon, who's playing Backgammon? Well, in your tree, in some sense, you're playing. You want to maximize the score. So actually, how many people know Backgammon? Okay, it's no longer a hit. It looks like this. Okay, you move these little discs around and you roll dice, and it's a thing. Okay, so so in Backgammon, you play. You decide like where you're going to move. Then who plays next, right? Then the dice play, right? Your opponent rolls the dice. So in some sense, they're out of your control. They're out of your opponent's control too. They're a random node, okay? What happens after the randomness? Now the adversarial thing happens. The opponent doesn't control the dice, but they do control their action. So there's a min node after that. Then come your dice. They play, right, in some sense, because you roll them and they're not under your control or your opponent's control. And then there's another max node. And so you have these kind of interleaved layers. And there are even names for this. They call this thing Expectimax. But you can forget all these names. There's just game trees, right? There's just the futures, and every node has a type. It's either max node because you control it, a mid node because it has adversarial behavior, or a chance node because it's something else, okay? So you can imagine the algorithm. You get to each node, you do your thing, and there's really nothing special about something like Backgammon once you have the general framework. Okay. Even though the kind of algorithm for Expectimax for Backgammon is something that you can immediately come up with, Backgammon itself is an interesting case study. Okay, and the reason why is because when the dice roll, what used to be a reasonable branching factor, there's only so many ways I can move my discs around, becomes much bigger because I need to think about all the ways the dice could fall. Okay, and because there are a lot of legal moves to begin with, and there are a lot of different ways the dice can fall, suddenly the branching factor is really large. And it's large in a way that's different from Go, right? In Go, there's just a lot of things the opponent can do, and you need to think about them all. Here, the issue is that as you go deeper into the tree, the probability of reaching a given node is going to shrink. And that's not just because it might not be optimal. It's because the probability of any particular future depends on the dice rolls that lead to it. So every part of the tree is kind of individually unlikely. And this is actually kind of bad news. And it's really the same issue as what happens why you can't prune Expectimax, because there's all this stuff that's all contributing a little. And so it's very hard to do search. So the usefulness of search on one hand is diminished because no part of the tree is really kind of controlling everything. But the good side of this is that limiting your depth ends up not actually being that damaging in some cases. So there's this historic AI called TD-gammon. TD stands for temporal difference. We'll see temporal difference learning when we talk about reinforcement learning in about a week. What TD-gammon did was a depth-2 search, which is already reasonably compute-intensive for the time, and a very good evaluation function that was actually learned, and we'll talk about how you can learn these evaluation functions in the coming weeks. And these two things together, reasonable depth search and a good evaluation function plus reinforcement learning, gave rise to a world champion level play at Backgammon. This was the first AI world champion in any game. Okay, so that's Backgammon. Let's talk about another generalization. So that was the generalization of what happens if your mins and maxes and chance nodes are all interleaved in some crazy way. There's a question of what happens if the game isn't a zero-sum game in the first place, or has multiple players, or both. So it's a generalized game. Okay, in a generalized game, we still have a tree. This tree is always there, because this is a tree of the things that might happen, right? It's just kind of always there. What changes is our assumptions at each node as to which child will be the actual outcome. But the possibilities are all there. So the tree is going to look like this. In this case, red's got 2 actions, then blue's got 2 actions, and then green's got 2 actions. Now, in a general game, right, in a zero-sum 2-player game, I get to the end of the game, and my utility is the number. Okay, if I'm playing against a minimizing agent, I don't need to think about their utility, because it's just the opposite of mine, meaning I can think about them minimizing my utility. But that's a very self-centered way to view the world, to just think that the minimizing agent is out to make you lose. That's not true. They're out to make themselves win, which happens to involve you losing in a zero-sum game. This isn't a zero-sum game. So everybody has their own utility, and everybody's maximizing their own. They don't care about anybody else's utility. They don't want other people to lose. They don't want other people. They don't care. If they did care about other people's utility, it would be encoded in their own utility. Okay, so all they need to care about is their utility. What does this mean? Well, let's think about what's going to happen. Let's look at this green node down here. What's green node going to do? Green's going to look, so let's look at this node A. A is going to look at its two options, right? And there are these two outcomes, and they're very different for red. Red's like desperately hoping for the outcome on the right. Green doesn't care. Green looks at this and says, as far as I'm concerned, including whatever it is I think about A's preferences, according to me, left is 6, right is 2, so A is going to choose this outcome. We know that's what's going to happen when A gets its hands on this state, right? We may not get here and play, but if we do, this is what's going to happen. And that means that the value of this state in some sense is not a single number, but 166, right? This is the vector of how the state is valued to all the agents, right? And so here at B, what do we get? Well, we get, it's going to choose between 1 and 2, so it's going to pick 6, 1, 2. So if you look at its choices, is red happy with its choices? Is red happy with green here, right? No, red is not. Red wishes green would do the other thing. Is blue happy with green? Yeah, sort of. At least kind of over on the left, blue is happy with green. And so in this case, so for example, over here, you can see that blue and green's components are very similar, and that means they're going to tend to pick the same things. And we know that when agents tend to have similar utilities, in the extreme case, they might have the same utilities, we know they cooperate. We saw that. And so what you're going to get in this corner of the tree is you're going to get cooperation, essentially blue and green versus red, right? And that means all kinds of things are going to emerge naturally that are cooperative behavior. But actually, if you look over on the other side of the tree, you can see down here that blue actually aligns better with red. And so here, kind of blue and green are actually at odds, and they're more like playing an adversarial game. And so a tree like this is going to naturally give rise to things like cooperation and competition at the extremes, but also all kinds of other behaviors will just emerge naturally because of how people's utilities do and don't align at various stages of play. Any questions about this? So each node, you look at your utility, and then other people either align or they don't. Okay. So let's do this. Let's take a quick break now, and now we're going to look at what exactly these utilities are and how we know there are numbers that we can even average in a meaningful way. So let's do a 2-minute break. Okay, let's start again. All right. So underlying a lot of what we've done so far is this notion of utility, which is a number that encodes the goodness of a state. And up till now, all we really needed out of these numbers was that bigger utility means better, right? We just started doing something very interesting. We just started averaging these numbers and assuming that somehow these numbers not only encode whether you like A or B better, but they even encode whether you want, some particular distribution over A and B, whether you can average these things in a meaningful way. And how do we know there are numbers that have this magical property that when you average them together, they still encode your preferences? Right? We kind of don't, so we need to stop and think about this for a while. So first of all, when we talk about utilities, the fundamental thing that a utility encodes is what an agent prefers. So at the base, you've got this agent, it likes things. So this agent here likes ice cream, but does not like, I guess, flowers or puppies. Don't know what's going on there. Anyway, so that's this agent. Agents can have any preferences they want, right? The question isn't whether it makes sense to dislike puppies. Some agents have that preference, some don't. The question is, are there numbers that can summarize those preferences? So, what have we been doing? We've been computing averages, and we haven't been doing things like minimax recently. We've been taking averages of utilities. So why shouldn't our basic principle be a principle of minimax utility? Remember in the first class I said, the summary of AI is you should choose the action which maximizes your expected utility. And we would unpack that definition as we go. And we're doing that now. So we know what maximum means. It means kind of search the tree for the best thing. We know what utilities are. And for the past hour, we've been averaging utilities. Why? Well, we kind of already know, right? That's why. You don't want to be minimax. If your principle was one of minimax utility, you would live in a kind of very pessimistic world where things you often make poor decisions because you think things are worse than they actually are. So our basic principle is going to be maximizing expected utilities, and that is basically the definition of a rational agent in this class. A rational agent is one that chooses an action that maximizes its expected utility given its knowledge. And we actually talked a little bit earlier in response to one of the questions about what exactly it means to have knowledge and use it in your decision. But we still have questions. Where do utilities come from? right? Do they come from the utility fairy, right? How do we know utilities exist? That is, how do we know there are numbers that kind of are well behaved with respect to averaging? And what happens if we realize that, for example, we're all human beings with complex kind of beliefs and preferences. Maybe we can't be described as utilities. What are utilities? They're functions from states of the world to real numbers. Maybe you feel like you can't be described as a function from states of the world to real numbers. You are not a real valued function. Okay. The bad news, by the way, is there's a theorem that says you are a real valued function. Okay. But let's build up to that. What utility should I use? For minimax reasoning, it kind of doesn't really matter as long as you get the magnitudes right. So let's take a look at two minimax trees. Let's take a look at two minimax trees here. Let's look at the one on the left. Right, we can choose between this 0 or 40, or we can go to the 20 or 30 route. Well, we're playing against a minimizer, so we know that if we go left, we're going to get 0. And we know if we go right, we're going to get 20, and so our value is 20. But the important thing is we should choose to go right, because that right has the highest minimax value. What if we had different utilities and we were playing minimax, right? So we're against an adversarial agent. Well, on the left, it's still 0. On the right now, it's 400, right? It's a bigger number, but we just changed the numbers. So that doesn't really mean anything. And now 400. So the numbers all change. What did I do? I squared them, right? The numbers all changed, but we still choose the same action, right? Minimax doesn't really change if you square the numbers or really do any kind of monotonic transformation. You can add 1 to the numbers. You're going to get the same outcome. Okay. But what happens if instead of doing minimax, we live in a world of averages, right? For average case reasoning, that's not going to work. Let's do averages. So in Expectimax over here, if they're even outcomes, right? So imagine each one's equally likely. Here, the expected utility is 20. And on the right, the expected utility is 25. So we should choose the right action. Let's go to this other set of utilities where they have the same order, but they've all been kind of transformed by squaring them. Well, now on the left, the average is 800. And on the right, the average is less than 800, okay? So we're going to choose the left. So that's a little bit weird. If you take these numbers, if kind of squaring them or taking the square root preserves the order but changes my decisions, then it matters not just what the magnitudes are, but the actual numbers. They have to kind of be calibrated in some way. So suddenly, maybe we're not so sure that there even are utilities that do the right thing when you average them, because squaring something, it doesn't really change them that much, maybe. All right, so let's go back and figure out where we're at. Utilities are functions from outcomes, which are states of the world, to real numbers that are meant to describe an agent's preferences. Where do they come from? They could be +1 or -1 in some kind of simple game, but whatever they are, they're going to summarize the agent's goals. There's a theorem that we'll see in a second that says any rational preferences, we'll see what rational means, but any rational preferences can be summarized as a utility function. So in general, what we do is we say, we're going to hardwire utilities and then let some behaviors emerge, right? This isn't the only way we could proceed. We could let our agents pick their utility functions, right? That's kind of a bad idea. Why don't we let our vacuum cleaner pick its utility function? Right? We say, your utility function is picking up dirt or something like that. Because, what if it decides it likes spreading dirt? Or what if it decides it likes being out of battery? I mean, you're not going to get a good vacuum cleaner. You know what you want it to do, so you hardwire that. The flip side is, why don't we just tell it what to do? Why don't we tell it, go left and then go right and then go left again or something like that? That's because the utilities are, in some sense, they're easy to specify. Pick up the dirt. Don't create more dirt, that kind of thing. But the actual behaviors are going to depend on the context. And so we want computation to give rise to the behaviors from the specification of the utilities. Okay, so back to utilities. Let's imagine we have an agent, and we know it prefers 1 scoop to 0 scoops, and it prefers 2 scoops to 1 scoop. So we know it likes more ice cream. This is an ice cream eating robot, and it likes to have more ice cream. So that's reasonable. But what should the utilities be? Should they be 0, 1, and 2, or maybe 0, 1, and 3 million, right? Who knows, right? Different numbers are going to give rise to different behaviors. But so far, just looking at more scoops is better. It's hard to do anything other than know that the numbers should be going up. Okay. Utilities, the key thing is you need to not only know about which kind of states of the world you prefer, which lets you give a monotonic ordering, but you also need to know how you feel about uncertain outcomes, meaning how you feel about being in a situation where multiple things might happen. So let's say I'm going to get some ice cream, and I have a choice. I'm this robot. I can get a single scoop or I can get a double scoop. Now, if I get a single scoop, then I'm reasonably happy. I get my single scoop. Everything always goes according to plan. And that's an outcome, and I kind of like that outcome. Okay, now if I'm going to compare using Expectimax this to getting double, well, I need to know what happens if I get double. But maybe there's two outcomes to getting a double. Maybe there's some chance you drop it, right? You got greedy, you piled the ice cream too high, now you're a sad robot, right? So what happens if it works? Well, now you're actually maximally happy here, right? You have your two scoops and you're a happy robot. Okay, so we're choosing between getting a single, which is this medium outcome, and getting a double, which could either be really bad or really good. Which one should we prefer? Well, okay, either answer is fine, right? Maybe your robot is risk averse, maybe it's risk seeking, who knows? Either preference is fine, but some utilities will tell you to go left, and other utilities will tell you to go right. So we have to basically figure out from our preferences over these things what the numbers need to be. All right, so that's the fundamental thing, preferences. An agent has to have preferences among things because it has to make choices. You can say, I don't care, but that's a preference too, that's indifference, right? So we know that an agent has to have preferences among prizes, right? So a prize is a thing, right? Like the ice cream cone with two scoops. That is one outcome. When we say prize, we don't really mean like, it's not like a game show where you get a prize. A prize here it's a formal notion that means a single state of the world. So you have preferences among states of worlds. But you also, whether you kind of know it or not, have preferences over what are called lotteries. And a lottery is not a lottery ticket. So whether or not you like a lottery doesn't depend on whether you like gambling or whether you like the thrill of scratching off the silver film or whatever. Okay, none of that matters. A lottery is simply a situation where you are unsure which state of the world will result, and there are probabilities associated with them, right? For example, not knowing whether you're going to get two scoops or drop your ice cream, that's a lottery. You're uncertain which of those two outcomes there's going to be. So lotteries are a collection of outcomes with probabilities associated to them. So in this case, the lottery shown here, L, is between two outcomes, A and B, with probabilities P and 1 minus P. Our notation, we write that we prefer A to B by kind of A greater than B, and A is indifferent to B as A kind of squiggle B. All right, so you have to have preferences amongst these, right? The question is, are there utilities that encode those preferences? Well, you could think that we could just figure this out by telling you all the possible outcomes and saying how much you like them. You like the two scoops, but you don't like better luck next time. So this idea about whether or not there are utilities that encode your preferences has to do with this notion of rationality that we have to define before we make any progress. Now, you may think rationality means coming up with a kind of very detailed plan, making your decisions in a fact-based way. This is kind of a common notion of rationality. When we say rationality in this course, we mean something technical. And when we say rationality technical, what we mean is that your preferences obey certain axioms, right? So not necessarily that you make checklists, but the following axioms. Here's your first axiom of rationality. And this is math. You can look at an axiom and say, I don't believe that axiom. And then you can see how well you get on in your theory without it. Okay, but here are some axioms of transitivity. One is the axiom of transitivity, which says if A is better than B and B is better than C, then you should prefer A to C. Okay? Who thinks this is a reasonable axiom? Right? It's basically reasonable. What happens if you don't obey this axiom? Can you have preferences that are intransitive? Of course you can. Right? So for example, you could be this kind of toddler robot, and maybe it prefers B to C. And so if it has C, you can it'll pay you a penny. You can take a penny and give it B. Okay, but if it prefers A to B, then it's willing to pay a penny to get A. But now it actually likes C better than A, so it's willing to pay a penny to get C. And now it's back where it started, minus 3 cents. Okay? So if you have intransitive preferences, which you can be induced to give away all of your money or all of whatever. So we look at this and we say, all right, while there are intransitive preferences, they're not really they're not good enough to get the stamp of rationality. So we take the axiom of transitivity as a requirement for this technical definition of rationality. There are more axioms. So orderability. If I show you A and B, you either have to like A better, or you have to like B better, or you have to be indifferent. That seems reasonable. You might get kind of weird behavior if you don't have that. So kind of check these things off. Transitivity we just talked about. Continuity. Okay, so continuity says that if A is good and C is bad and B is somewhere in between, then there should be some lottery between A and C at which you're indifferent between that lottery and B, right? Some mixture of the good thing and bad thing should equal the middle thing. Okay, now which mixture, which exact probability? Okay, we'd have to figure it out. But there has to be some probability where you hit break even. If P is 1 in this, then you get A. Sorry, if P is 1, you get A, and that's better. If P is 0, you get C, and that's worse. And so at some point, that slider should hit break even. That's the axiom of continuity. Okay? Substitutability says if you're indifferent between A and B, you're indifferent between lotteries that differ only in whether they have A or B. That seems reasonable. And monotonicity says if you like A better than B, then lotteries that have more A are better than lotteries that have less A. Okay, do you like these axioms? Formally, we say if you have all of these axioms, we have a theorem that says rational preferences, meaning preferences that obey these axioms, can be described as the maximization of some expected utility function. There's some utility function such that the expectation works out. If you obey all of these, you get the stamp of rationality. Now, you could look at this and you'd be like, okay, no, this doesn't seem right to me. I don't agree with these axioms. Is there any axiom here you don't like? These seem basically harmless. There is an axiom here that not everybody agrees with. Which one do you think it is? It's actually continuity. People have problems with continuity sometimes. Because what if C is so bad that even the slightest bit of C, if it's not 0, is enough to make the lottery terrible? So in some sense, continuity also involves something about boundedness. So sometimes people worry about continuity. But basically, these are reasonable, and these are our axioms. Okay, so the maximum expected utility principle. Here's what backs it up. There's a theorem that says if you have preferences which meet the axioms of rationality, some preferences don't, then there is a real valued function with the following amazing property. 1, the utilities you assign to states put the states in an order that respects preferences. So you kind of capture which states you prefer. But even more amazing, your utility of a lottery is the average, the expectation, of the utilities of the prizes inside that lottery. And what that says is it says the values that you assign preserve your preferences both over prizes and lotteries. And that's kind of amazing. So if you feel like you can't be summarized by a utility function, then there must be one of those preferences you don't like. And then you have to decide which one it is. Okay, so the MEU principle says you choose the action that maximizes your expected utility. And of course, as we've said before in this class, an agent can be rational, meaning it chooses actions consistently with this principle without ever manipulating utilities or probabilities. So it doesn't say anything about how you compute, just that your performance has to be, that your actions have to be consistent with this rule. Okay, let's talk about human utilities, right? And there's an interesting thing here because really when we talk about this utility stuff, we've been talking about robots and how to get robot vacuum cleaners to do things, but actually this is very relevant for humans and human decision making. And a lot of the study of utilities came out of economics and long before we were trying to figure out how to make robot vacuum cleaners. So let's talk a little bit about what kinds of utilities humans have, how we figure out what they are, and then what you can do with them. Okay. So first we need a scale if we're going to have utilities, right? Pac-Man operates in points. You might want the expected points to be high. What are your points, right? Life doesn't come with points, right? You could say, oh, there's money. Well, there's issues with using money as a utility function, but I suppose that's one possible scale you could try to use. We'll see why it's a bad one in a couple slides. So what do people use? So what people use, there's normalized utilities. This is kind of, in some sense, the cop-out scale. Utilities goes from 0 to 1. Great. That doesn't tell you much. There's a thing called a micromort. Okay, what's a micromort? A micromort is a 1/millionth chance of death, right? Do you want a micromort? No, you don't want a micromort. So you would like to have as few micromorts as possible, right? And this is useful for talking about product risks, where there's like a risk of something bad happening and you're balancing these things in some kind of decision theoretic way. There's a related thing called quality adjusted life years, which tends to be used for medical decision making when there's a lot of risk, because now you're balancing not just how long you might live, but the quality. These are by the way, the reason these things are kind of so like deeply serious is because a lot of where this utility theory really comes into play is in making very hard decisions about kind of very tricky trade-offs between these weighty kinds of things. Okay. There are multiple scales. That shouldn't really worry us because behavior of these things is invariant under positive linear transformation. You say, but wait a minute, you squared everything and it messed everything up. How do we know this is okay? Well, they're expectations. Expectations linear, so as long as you do something linear, you're going to be okay. But as soon as you square things, then you're going to break all of your expectations. Okay. If all I do is show a human deterministic prizes, and I don't ever ask you about mixtures of things, I can figure out that you like 2 scoops better than 1 scoop, but I can't figure out whether you like it twice as much. Because in order to figure out things like that, I need to ask you questions about maybe getting 2 scoops or maybe getting 0. Okay, so if you actually want to know human utilities, you have to start talking to people about lotteries, and that gets tricky. So let's actually talk about how you'd figure out human utilities. Well, utilities map states to real numbers. Which numbers should those be? Here's one way people assess human utilities on, say, a 0 to 1 scale. So I'm supposed to be able to take anything like a new computer or getting an A+ or whatever, and you have to assign some numbers. The new computer is 0.2 and the A+ is 0.3. How are you supposed to figure these things out? Here's how people do it. They ask you a question. Do you prefer A or B? Right? It's just like getting new eyeglasses. Okay. So the thing that you get asked about has to do with some question where we compare the thing we're getting a utility for, right? A new computer, or whatever it is, right? We compare that prize to what's called a standard lottery, right? And the standard lottery involves you being unsure whether you'll get one of 2 things, one of which is very good and one of which is very bad. And we manipulate the probability until you kind of think that lottery is about the same as the prize, and that's somehow a measurement of how much you like that prize. So here's an example. Okay, pay $30. That's a prize. Okay, it's actually more like a parking ticket, right? You lose money with this prize. Okay, do you want to pay $30? No, you don't want this. So we're trying to figure out how bad it is, right? So what we do is we say, all right, you don't like that. Let's talk about the lottery, meaning you're not sure which of these 2 things is going to happen, where one of the things is no change. What would you rather have? Pay $30 or nothing changes? You'd rather have nothing changes. You don't want to pay $30. On the other hand, let's think about something worse than paying $30, like instant death, okay? I hope we can all agree that paying $30 is somewhere between nothing changing and instant death. It's more like nothing changing, hopefully. And so what we do is we manipulate the probability until you say, yeah, okay, I think that lottery is about the same as paying $30. Okay, well, what is that number? They do this on a lot of people, and it turns out $30 is about, 1/millionth chance of instant death. Right? At some point, the chance gets so low, you're like, okay, I'll take the very, very small chance of instant death before I'll pay the $30. And obviously, a very small chance, but there's, there you go. The 1 micromort costs, I guess, $30. Okay, negative $30. Okay, so this is one way to get utilities in 0 to 1, and of course, this thing here has a kind of very small utility. That's a small thing. Okay, let's get back to money for a second. So money, it turns out, is very tempting to think, all right, well, like to the extent that life has a keeping score, you might think it's money, but money really doesn't act like a utility function. We can, however, talk about the utility of money, right? Obviously, money has some utility. And so here are some concepts that help us think about the difference between utilities and money. Well, we can talk about a lottery. And again, even though there's dollar signs, this lottery is not actually kind of getting a lottery ticket. Because one reason you might like getting a lottery ticket is it's fun. Or you might hate it because you just feels hopeless or something. Those things are not what's being tested here. A lottery is just uncertainty over 2 outcomes. So a lottery might be, with probability P, you get X dollars, and probability 1 minus P, you get Y dollars. For example, you have a bike and it might get stolen, right? That means you have a lottery between kind of the bike and not the bike, right? With some probability that reflects how likely it is to get stolen. Okay, a lottery has an expected monetary value, okay, if it's a lottery over dollar amounts. The expected monetary value of a lottery is what you get when you take the average of the dollar amounts, okay? The utility, however, is the average of the utility of the dollar amounts. Okay, it's typically the case that the utility of a lottery is lower than the utility of the expected monetary value. Let's see an example. Okay, let's see this example first, and then we'll go back. Okay, so here's a lottery. This is a lottery where you have a 50% chance of getting $1,000 and a 50% chance of getting none. Okay, you don't know which. Okay. What is this thing's expected monetary value? 500, easy. Okay, what is its certainty equivalent? What's that? That's the amount of money that you would accept in exchange for this lottery, right? This lottery is a reasonably good thing, right? You either get no dollars or $1,000. Like, it's reasonably good. Okay, how much money would you take for this lottery? I'm willing to take this lottery off your hands. How much do I have to pay you? Okay. How many people would give up this lottery for $500? Okay. How many people would give up this lottery for $4? No one. How about $300? How about $400? Okay, it turns out the kind of most common answer for this when they do this is about $400. So most people will trade this kind of 50% chance at $1,000 for a guaranteed $400. Some people, the value's higher or lower, and that's totally fine. Okay, the difference is the reason why there's an insurance industry. The difference is what's called the insurance premium. The reason there's an insurance industry is you have all kinds of lotteries, like bike or not bike, because your bike might get stolen. You don't want this lottery, okay? And so you trade the lottery with the insurance agent, with the insurance company, where the insurance company gives you guaranteed bike, okay, but takes some of your money. So the fact that you've got an insurance company that wants this lottery, but you would rather have $400, everybody wins, right? Because they give you $400 and they take your lottery. Everyone's happy. Okay, if people were risk neutral, there would be no insurance really involved. Okay, let's go back to this important graph over here, which has to do with kind of risk adverseness. So here's dollar signs going in this direction, utility going up. All right, as you get more money, kind of presumably the normal case is more money is better. And so as your money increases, so does your utility. But it's not linear, right? Doubling your money doesn't double your utility. Why not? Well, okay, let's see. How many of you would like $1 billion? Most people would like $1 billion. Now, what would you do with $1 billion? All kinds of stuff, right? But now think, if you had $1 billion, how much more useful would your second $1 billion be? Like, right? Not so much new you can do with the second $1 billion. The fact that the second $1 billion is a smaller increase in your utility than the first means that your utility has to be kind of sublinear in money. That is, like, eventually there's nothing more to buy or whatever. For whatever reason, we know utilities are going to be bounded above, remember continuity. And so as you get more money, sooner or later you have to kind of hit the cap. And so the utility has to look like this. And in the other direction, kind of once you're kind of $1 billion in debt, you're too big to fail, right? So the utilities have to kind of asymptote in both directions, and that gives rise to a typical behavior of risk aversion with respect to money on the positive side and being risk prone on the negative side. Of course, then there's details like if you don't have this much money or greater, you can't buy the new computer, and so smaller amounts just aren't useful to you. So there are reasons why it might not be some simple function, but at the kind of a broad scale, there's diminishing returns in both directions, because there kind of have to be. All right, so we talked about lotteries. And remember with lotteries, this is actually a kind of important point. It is actually win-win, right? When you get bike theft insurance or something, it's not like you've just been scammed, right? You are actually happier, and so is the insurance company, because they have lots of lotteries, and so essentially what they have that you don't is the law of large numbers. So their utility curve is kind of much flatter, and you're happier now because you have the certainty equivalent. Okay. Let's look at an important example here. So when we talk about probabilities and reasoning and rational inference and things like this, we very quickly get into questions about, okay, we're trying to build computers that are intelligent. We have humans that are intelligent, and there's always somebody who says, okay, yeah, but are humans really intelligent? Because look at all the dumb things people do sometimes. Okay, so here's an example that really gets to the heart of the argument, and it's not going to answer the argument, but this gets to the heart of a kind of the argument of are humans rational, are they optimal? Now, of course, there are cases. If I asked you kind of what's the square root of 312, like, it's going to take a while to get an answer, and you're probably going to be a little bit off, and that's okay, right? This isn't about that. This is about kind of trade-offs and whether people are good at making decision theoretic trade-offs as things relate to them. So here's an example. This is an example from the 50s. So here's a lottery, right? You have a choice between two things. You can pick A. Okay, if you get A, you have an 80% chance of $4,000 or a 20% chance of 0. Okay? You can pick B, where you're guaranteed $3,000. Who prefers A? Who prefers B? Okay, most of you want B. Yeah, B looks pretty nice. Okay, let's look at some other lottery. Okay, this is C. These are two other lotteries, and your choice is between C or D. So let me just mark here that everybody liked B. Okay, everybody liked B. Okay, C says you get 20% chance at $4,000, but probably nothing. Or you can have a 25% chance at $3,000, or probably nothing. Who prefers C? You can do some math if you want. Who prefers D? Okay, so you preferred B to A, and you preferred C to D, which is like basically what everybody prefers if you ask this question broadly. Most people prefer B to A. Most people prefer C to D. Okay, here's the tricky thing, though. Let's say the utility of $0 is 0. And that's fine, because we can always do kind of we can always do positive linear transformations, so this doesn't change anything. What do we know? We know that if B is better than A, which you just told me it is, then the utility of $3,000, whatever it is bigger than 80% of the utility of $4,000. That's what the lottery says. And that's fine. There's nothing wrong with that. The $3,000, it just means you get this diminishing returns. $4,000 isn't that much better, and so being guaranteed $3,000 is better. That's fine, except now look at C and D. If C is better than D, you actually get the opposite inequality if you work out the numbers. Okay, so possibility 1 is CS188 students, along with just about everybody else in the world, are in fact irrational. Right? You do not make decisions. And now I'm saying something technical. I'm saying that your decisions are not consistent with preferences that obey these axioms. Right? You've got some weird kind of asymmetric thing going on. Yes, comment. It is, so the question is, why is it 0.8 in C and D? It's really kind of 0.25, and then you would scale everything up. All right. Other questions? So are we just going to give up and admit that we're irrational and need to be replaced by machines? Okay. Yes. You know you're in front of a computer science audience when the answer is yes. Okay, so, okay. Here's the thing, though. You can say this is an issue of human rationality, or you can just say it's an issue of not correctly modeling the choice. So really, you could say the issue, there's one of these outcomes that's different than all of the rest. One of these outcomes, like look up at A and B. Let's take a look here. This outcome here, the 20% chance of getting $0. You actually get something else. Something else happens when you have this outcome other than getting $0. What do you get? How do you feel? You feel stupid, right? Because you have the chance of getting this guaranteed payoff, and you got the 0. So actually you get $0 plus feel stupid, right? You don't like to feel stupid. Therefore, this outcome actually has a lower utility. And if you kind of include dollars plus stupid feeling, maybe this all works out rational. So I'm not going to settle this here, right? Because you can then come up with more complicated examples. People argue about this. But the point is, this question is very tricky, whether it's that humans are sometimes irrational or whether we're not very good at stating what preferences humans are maximizing. It could very well be that somebody is very optimally maximizing preferences that you think are deeply weird. It doesn't mean they're irrational, it means their preferences are weird. So next time you get into an argument, don't tell somebody they're being irrational, tell them their preference function is deeply weird. Okay. All right, we'll pick up next time with Markov decision processes.